Thank you, Brent. Good day, everyone. As introduced, my name is Mante. I'll be co-presenting with Olga. We will look at the battery metal extraction using ion exchange. The consistent theme with all the presentation is that in today's technological world, portable power supply has become necessary and rechargeable batteries, which are more durable, are more critical than ever. We rely on batteries to power our electronics like mobile phones, laptop, and so much more. The top market drivers for battery minerals and metals have already been discussed. The main point to highlight here is that battery manufacturing relies on a set of raw materials with specific technical properties, different chemistries for batteries, whether be it nickel metal hydride, lithium ion, vanadium redox flow, or other emerging technologies, each require raw material inputs with distinct attributes. The raw materials used in battery manufacturing are a source of metals such as lithium, nickel, cobalt, and vanadium, which are used as precursor in the battery manufacturing process. To understand how these metals are vital in the battery manufacturing value chain, we will just summarize it to try and have context. So the value chain is comprised of three segments, which is the upstream, which consists of the raw material and their processing, midstream, which comprise of the various manufactured and the assembly, and downstream, which includes assembly of those components. So crystallized nickel, cobalt sulfates, or chlorides with high purity with high purity requirements are typically used in the battery industry as starting point for active cathode preparation. Nickel and cobalt crystals are produced from raw materials such as nickel laterites, copper and cobalt ores. These raw materials are typically leached, and the pregnant leach solution that is generated, it's purified. The typical purification technologies that are used is normally precipitation, solvent extraction, and crystallization, including also ion exchange. The purified concentrated metal sulfates or solutions are then evaporated and crystallized to form metal sulfate crystals as end products to be used in precursor manufacturing process. Managing the impurities properly along the whole manufacturing value chain is essential in meeting the purity requirements for battery raw materials. Hence, purification technologies such as ion exchange can play a vital role in meeting the required impurity specification for precursor manufacturing process. So what is ion exchange? So ion exchange is a reversible chemical reaction where an ion from solution is exchanged for a similarly charged ion to an immobile solid particle. To recover metals from solution, ion exchange resins are typically used. The resins are an insoluble matrix which are highly porous, and they've got functional groups attached onto them to allow for selective recovery of metals of interest. Ion exchange technology is widely used in hydrometallurgical flow sheets. Ion exchange can be used for recovery of for primary recovery of metals from difficult to filter slurries. Ion exchange can also be used as a metal recovery for concentrating or upgrading dilute PLSs from heap or agitated leach tanks. Ion exchange can also be used as a polishing or impurity removal technology for electrolytes, more widely used in the polishing of base metal electrolytes. On a commercial scale, one can use a range of processing vessels as ion exchange conductors. The various processing vessels have their own strengths depending on the application. For example, fixed bed ion exchange can be used for dilute clear solutions, where fixed bed can be operated in a downflow and achieve higher volumetric throughput. For difficult to filter solution, resin in pulp can be used to minimize metal losses due to entrained solution to the tails. For more complex separations, ISEP contactors can also be used. Multotec, in collaboration with Cleantech, offers moving bed ion exchange systems, which provide added a benefit in terms of resin utilization and inventory. They provide an added advantage when coming to elution, where there is an optimized reagent utilization and generation of small volume liquor. Clean ion exchange metal recovery technology provide a continuous countercurrent approach to ion exchange, thereby optimally exploiting ion exchange resin chemistry to deliver richer metal liquors and improved water balance around the circuit. So an added advantage of the clean ion exchange technology is that each and every step of ion exchange is done in a designated column. That is adsorption wash, elution, and elution wash. It's done in a designated column to maximize the use of resin. Airlifts are used to advance resin in between the vessels. Some of the conventional designs will use eductors and pump to advance resins through the column. However, this can be detrimental as it can affect the mechanical properties of the resin, resulting in resin losses. So the moving peg bed is versatile. It can achieve countercurrent movement of solution and resin. Here on the pictures is the different columns that are used for adsorption wash, and also for an agitated pachuca that can be used for elution, for systems that contain gypsum that has formed during elution circuits. And a novel, also just to add on, with the ion exchange contactors, a novel column that is offered is the U column, which is a specialized elution column that is used to deliver richer liquors that can be used for subsequent unit processing, such as electrowinning and crystallization. In summary, just to summarize what are the advantages of clean ion exchange, is that the periodic movement of resin allows for high tolerance of incoming solids. The ratio control between the resin and the volume allows for high tolerance of variable feed composition, thus ensuring efficient polishing. The countercurrent configuration allows for full optimization of the resin loading capacity and selectivity, plus guarantees the efficient volume guarantees for efficient value for metal polishing. The cost benefit of clean IX for clean IX technology is that, one, it provides OPEX savings in terms of reagent efficiency. Because of the minimized resin inventory, it allows for CapEx savings, as it allows for the first fill of the resin to be much cheaper compared to conventional fixed bed ion exchange. I will now hand over to Olga, who will take you through the various applications of clean ion exchange technology in battery metals processing, mainly taking you through the flow sheets that have been developed using this technology. Thank you.
Thank you, Mante. So now I would like to take you through a number of case studies where Cleantech introduced its moving bed ion exchange technology. One of the leading cases is recovery of nickel and cobalt from high pressure oxidation leach slurry of the nickel laterites. Usually companies are considering to introduce, after leaching, multiple filtration units which results in quite diluted streams, losses of the value metal. In the flow sheet which Sunrise project is implementing, they use continuous ion exchange, resin and pulp, to recover bulk of nickel and cobalt, purify to an extent, upgrade, and provide a subsequent feed for the further refinery via solvent extraction technology. For example, the demonstration pilot plant, which was run in 2018, was used to showcase that resin and pulp technology can recover nickel and cobalt efficiently, like 99% recovery, from the difficult to filter pre-neutralized pulp coming from the pressure oxidation leaching. And metal were first upgraded onto the resin. And then when the elution was done in the U column Mante was mentioning before, we generated a very rich nickel cobalt liquor, which was then subsequently used for purification, separation, and production of nickel and cobalt salts, which met requirements of the battery market. So implementation of this technology allowed to improve the overall recovery of the nickel and cobalt, almost avoid the loss of the value metal into the residue, and also the size of the refinery circuit was much smaller if you will compare it with some of the alternative flow sheets which are currently in use. One of the other applications I would like to talk about of ion exchange is when certain impurities, it has to be removed from the bulk of the metal. Like, for example, to achieve a high purity of cobalt, some impurities like zinc, lead, and copper had to be removed like to below a couple of ppms or even micrograms a liter. So for one of the client, we had to remove cadmium and zinc from the cobalt liquor from 18 ppm in the case of cadmium, for example, to below 20 ppb. And this was achieved with moving bed technology. And as the desorption was organized in the U column, this allowed us to minimize cobalt loss into the impurity bearing stream, and also significantly decrease the amount of cadmium and zinc which had to go back into the main impurity removal system. So in comparison with fixed bed application, or for example carousel application of ion exchange, moving bed technology allowed to decrease resin inventory significantly, and also provide impurity bearing streams of a composition which would be much more easier to manage in comparison, from the point of view of the flow and of the grade downstream. Because, for example, fixed bed technology will generate liquor which is at least 3 times more dilute, and that's mean the size of your tanks and precipitation circuit would be much bigger. One of the other technologies I want to talk to you about is about vanadium based redox batteries, which currently like pretty new technology, I would say, but the market is growing. The vanadium batteries are meant to be used for storage of the energy, and I believe that for South Africa this technology can be pretty attractive, taking into account your Eskom issues. So Cleantech developed a process for vanadium recovery from a certain type of streams, and when ion exchange was used for recovery, upgrade and purification, which allows within a single unit of operation to produce exactly after the leaching, to produce the battery-grade vanadium electrolyte with a high purity and required concentration. So this process was used not only for the primary recovery from the leach liquor and producing the battery grade product, but also we did demonstrate that it can be used to purify the technical grade V2O5 or technical grade ammonium metavanadate salt. So technically, ion exchange plays a refining function and upgrade function at the same time. So there is a number of applications and options where ion exchange technology can be considered and can be much more beneficial than alternative technologies. We are open and we are eager to assist the clients in flowsheet development. We can support the test work program just as a consultant, or also providing the equipment or prototype equipment or mini scale equipment for the pilot plants and demonstration scale equipment as well. We open to very smooth collaboration, and we are always in touch with resin suppliers, engineering companies, and hydrometallurgical laboratories. Thank you. Any questions? You're welcome.